Well, according to my clock, it's now the appointed hour. So welcome once again to everybody. I trust everyone can hear and see. We're going to talk today, the second round on what is prior use justification. And as from the results of this morning's session, this is obviously a hot topic with many people having differing views and opinions. And obviously this is an area of great interest. I would ask, if you do have questions, I will address all the questions at the end, but feel free to type in your questions, and then I will go through all of them at the end. And that way we can spend more efficient time. Now, I know some of you are regular attendees of the Exida webinars, but some of you might not be. So if you indulge me for a minute or two, I'll just explain a little bit about the company. Actually, this year is our 20th anniversary, and we had a big party planned for March. And we were going to have our people come in from around the world. But of course, COVID-19 put paid to that, and unfortunately we had to suspend and cancel that. But anyway, Exida was formed 20 years ago by two people who were very active in the safety world at that time, Rainer Faller and Dr. Bill Goebel, and they decided to start Exida to help manufacturers initially understand what the new standard IEC 61508 was all about and how they could get their products certified. So since then, since starting with product certification from a safety aspect, we've grown exponentially over the last 20 years. We now also do certification from a cybersecurity point of view from IEC 62443 for products, and we also do personnel certification. Some of you may even be CFSEs or CFSPs, Certified Functional Safety Experts or Certified Functional Safety Professionals. And we've recently, in the last few years, introduced the Controls Automation Cybersecurity Expert and Controls Automation Cybersecurity Specialist, which are the equivalent of the CFSE and the CFSP. We also provide full lifecycle support services for the three main disciplines that are linked, very heavily linked to overall process safety, which of course is functional safety, alarm management, and cybersecurity. So these three all have similar life cycles. They all have an analysis phase, they all have a design and implementation phase, and they have an operations and maintenance phase. So we provide full life cycle support services for that, including all the training for alarm, functional safety, and cybersecurity. To support us, we have a comprehensive suite of tools to provide us with the ability to support the life cycles, and it's called Excellencia. And again, some of you, I'm sure, are very familiar with Excellencia and have used it. But we can now do support for cybersecurity, risk analysis, risk assessments using our CyberFacts tool, and of course the alarm management tool. We are global, as you can see, and as I said, we were hoping to have a nice party, but that didn't happen. We operate in various different industries. Our Germans operate in the automotive industry, and more recently we've been into robotics. Robotics is another growing area, autonomous driving vehicles and autonomous machinery. You may have been in the supermarkets and seen those tall little cleaning robots wandering around doing. And so this is all part and parcel of that. And also more machine safety. Machine safety seems to be picking up more now, because I think the industry is recognizing that machine safety is an important aspect to safeguard their employees, to prevent fingers or hands being amputated by machines or crushed. So that is definitely picking up. A bit about me, I've been around for 43 years now. And again, some of you may know me, some of you not. I started off life as a design engineer, designing hardware and software. Software in those days was fairly early on. doing control systems, and then moved into the safety system world with ICS in England, doing emergency shutdown, fire and gas, and addressable fire detection systems, amongst other things. And I spent nearly 20 years doing that. Then I went into the automation world, and I was doing power automation. And then about 8 years ago, I came back into safety with Exida. My primary role is to lead the end user services business, but also I'm one of the primary instructors for the functional safety course that we have, the FSC 100, as well as the cybersecurity classes we teach as well. I'm also responsible for our global business development. So how do we measure our success? Well, since starting with the 2 owners, we're now mostly employee owned. We have over 100 global experts worldwide. We've done more than 1,000 certification and assessment projects and modeled well over 500,000 CIFs using the Excellencia tool. The certification, as I mentioned, is targeting at product certification, but also personnel certification. And when we look at the functional safety and the cybersecurity, they both involve detailed analysis of the engineering process and what defense mechanisms from a cyber point of view are in there for network robustness, for example, and hardening. And then from the functional safety side, looking at both the engineering process and the design margins. We are one of the leading players now in the logic solver market. And typically 2 out of 3 devices that are certified have been certified by us. So again, somebody once told me we're probably the best kept secret because everybody thinks that TUV is bigger than us, when in fact it's not true. Reference materials, we've authored quite a lot of books. You can get these through the website, the exida.com website. But the other thing is we provide a lot of information free of charge. These webinars, for example, plus there are white papers, and there's the SAEL, which is the Safe Automation Equipment List, which gives you a list of typical devices that are certified under certain categories. You can look under logic solvers, you can look under sensors, either pressure transmitters, whatever the type of device you need. You can probably find one, or if not a generic one, in the SAEL. The data that's in the Excellencia tool is what we call the SERH, which is the Safe Equipment Reliability Handbook, and that's all the failure rates. So you can either get it with Excellencia, or if you just want to have the books, you can purchase the books. So Excellencia, as I said, is the primary tool that provides different features and functions. You can either have some of the tools as standalone. For example, the PHA tool, the fax tool, can be a standalone, or the LOPA tool as well could be a standalone, or they can be used as part of the suite. And we can import it from other tools such as PHA Pro and PHA Works into the fax tool, and then once it's in here, it can migrate all the way through these other tools, all the way out to the end. Even if we have chosen alarms as being possible layers of protection in the PHA and LOPA, if we decide that that's what we need, then they can be imported into the SIL alarm tool to start building a master alarm database. And then the SILstat tool is the field monitoring tool for being able to run the proof tests, document the findings, and also the performance of the protection layers, both SIS and non-SIS. It also helps with monitoring the mechanical integrity so that you can set times for when devices need to be refurbished or replaced as they get to the end of their useful life. And how we can do that is because we've redesigned our database so that the data can flow all the way through. So you can go from the hazard and risk analysis all the way through to the field for the event recording. We can generate proof tests, if necessary, out of the design automatically through Excellencia. And these are based upon the manufacturer's recommended proof tests that you'll find in the safety manuals. Okay, so that's the introduction. Let's get to the meat of this thing, which is 1511 and prior use justification. So one of the purposes of prior use, and this was an interesting point that came up this morning, is that prior use is to help us justify the device from a systematic point of view, to make sure that there are no inherent design flaws or potential issues that could cause a failure on demand. But that's not the only thing that we have to also be able to show. We also have to be able to show that if it's going to be used in a low demand application, that the PFD average can be met for the target SIL. So it's not just the systematic. We've still got to make sure that the reliability for the random failures can be met. And we come back to this very popular pie chart. Some of you may be very familiar with this, some of you may not be, but this was a study that was done by the Health and Safety Executive in the UK back in 1995, and they repeated it again in 2003, some 8 years later. Unfortunately, what they found is not a lot of difference in the split. They were still seeing a high proportion of problems coming from specification. So of course, these are all systematic type problems. And usually when I teach the FSE class, one of the things I do is I like to characterize, because I find it easier to remember these things. I like to characterize systematic as being the 3 Ps. So the first P, of course, is people. So from our people point of view, are they properly trained and are they competent to do the work that they need to do? 1511 now requires that we define roles and responsibilities, and we have a system in place to be able to track and monitor competency, to make sure we have competent people for the relevant tasks they have to perform in the life cycle. And so that's the first P. The second P is, do we have procedures that are being followed? And in the case of quite a few accidents, it was proven that the startup procedures were violated by the operators. So again, if a procedure is not worth following, then it's either the wrong procedure, in which case we need to have a better one, or it needs to be modified if people don't understand what it is. So the procedures are very important. They have to be clear, concise, and we have to make sure they're being followed. And then brings us to the third P, which is the paperwork. Do we have an audit trail? Do we have a paper trail that says this is what we're doing? We're actually doing what we said we were going to do, and we can prove it. So any one of those failing can lead us to a systematic issue. When it comes to 1511, 1511 is built around a life cycle. And again, companies that come under the OSHA PSM requirement in the US, in other words, if you have 10,000 pounds or more of anything that's highly toxic, corrosive, it's an asphyxiant or it's explosive, then you have to follow the OSHA requirements for PSM. In the UK, it's COMA. And 1511 and the old ISA 84, which is now ISA 61511, is recognized as being what we call RAGAGAP. So both COMA and OSHA require companies that come under their auspices that they follow RAGAGAP, recognized and generally accepted good engineering practice. Some people say best practice, but RAGAGAP is what we usually mean. So 1511 is built around a safety life cycle that has the 3 phases I mentioned already. We have an analysis phase, design and implementation, and operation and maintenance. And the whole point of the safety life cycle is to help us balance the risk against the reward, and that is making sure that we have a design that's been built upon sound principles. So we've done our risk assessment, we know what our tolerable risk is, and we're designed to meet that and to achieve optimal performance and cost. Now, one of the other things that is also a potential issue is the overall corporate culture. And corporate culture can play its role in the systematic, because if it's squeezing operations so that they have to cut costs, they have to cut manpower, They can't spend the amount of time they need to be able to do maintenance properly. If all of this has been driven by a bottom line focus, then it's going to be very difficult to implement this successfully or even implement it to meet the risk requirements. So the objective, of course, is to try and eliminate as far as possible any systematic faults, being those 3 Ps. And then, of course, we want to be able to design to make sure that we have reduced the potential for random faults. So we have a very dependable design. And when we look at the life cycle, what happens is when we finish the end of the analysis phase, we've identified the hazards, we've identified the consequences and the likelihoods. We've done our layer of protection analysis, so we know what how much risk reduction we need to achieve beyond what we already had. So that would then determine whether we have any safety instrumented functions and what the SIL targets are for those safety instrumented functions. And we capture all of that in what we call an initial SRS, a safety requirement specification, sometimes called the process SRS. And that's what we use to feed into the design phase. So when we look at the design phase, one of the first things we have to do is think about the technology we're going to select for our safety instrumented functions. And of course, what we have to do, according to the requirements of 1511, is justify that selection. And the justification is very important because we need to make sure that the systematic capability for the SIL, as well as the application and reliability requirements, are met. So we should be selecting the equipment that we need to perform the task. So that means it's either going to be selected on the basis of IEC 61508 certified products or what's known as prior use justification. Now, for example, IEC 61508 talks about proven in use, and some people mix them up. They mix up proven in use with prior use justifications. So what's the difference between the two? Now, I didn't put this slide in this morning, and I just explained it, but after some of the questions I got, I figured I should put this in the slide. So proven in use is based on the manufacturer's design basis. In other words, what the temperature rating was, the vibration limit, the corrosion limit, and any desired maintenance support for the device. That's from the manufacturer's perspective. But for prior use, this now has to deal with the installed performance within a process application, which will be for a given or a specific operating environment, which is very often different than the manufacturer's design basis. So this is the difference between the two, and this is defined and called out in 1511 under clause 3.2.51. So again, I didn't have that in this morning, but I thought I would put it in for this afternoon so that people will see the difference and understand the difference between the two. So the other thing we have to remember is for equipment justification, we also have to consider the application requirements. So are we using this device in a way that we should be using it? And secondly is the safety integrity requirements. What's the SIL that we require? So both of these need to be met and not just the systematic capability. Now, of course, when you use an IEC 61508 certified device, there is a certificate that states what the systematic capability of the device is. And if it has a systematic capability of SIL 3, then you can use that in a SIL 1, a SIL 2, or a SIL 3 application. But the thing to remember about the certificate is that, number one, is it coming from a credible source? And is that, if it's a third party, is that third party accredited to do that work? And what you should look for on the certificate is an accreditation body logo. If you look on an exida certificate at the bottom left-hand corner, you'll see a blue and white ANSI logo. So basically, ANSI is the accreditation body for North America, and we are accredited by ANSI to be able to carry out certification. So if we do this, we have to document the justification. So from a 1508 point of view, it's easy because we can use the certificate as part of the documentation and the justification. But for a prior use justification, that's a different story. So the first thing we need to look at is, does it perform all the needed functions that we require? And that's the same in both cases. Is it rated for the expected environment? So again, if we didn't know that this thing was going into Alaska and we hadn't got it rated for those temperatures, or if it needed heat tracing and we haven't got that, then we're going to have a problem. Are the materials compatible with the expected process conditions? So here again, if we're considering a valve or a final element, then what's the service? Is it clean service? Is it severe service in terms of is it corrosive what's flowing through there? What type of material is it? Is it abrasive? Because if we don't select the right device with the right materials for the application, we're going to end up with much higher failures. And the other thing is safety manual restrictions. Now, it doesn't matter whether we're using a SIL certified device or whether we're using a device that's either proven in use or we want to do a prior use justification, because in both cases we need to have a safety manual. The safety manual has specific information that is required for being able to apply it to the SIL that we're looking at. And there could be restrictions. And I always say to the class that if it says SIL 2 capable, there's that nice word capable. What does capable mean? And it may mean that if you're trying to achieve SIL 2, that you may need 2 of the devices and they may need to be configured a certain way, or they may need some sort of interface. But you won't know that unless you have the safety manual. So for manufacturers claiming proven in use, they still have to have a safety manual. When it comes to the prior use justification, we need to make sure we've covered our bases and we've got everything we need. So some of the general requirements: demonstrating the SIL capability of device based on previous operating experience in similar operating environments. So here again, it has to be similar. And the other thing is, of course, that we're trying to gather from a prior use justification evidence that dangerous systematic faults have been reduced to a sufficiently low level. So what this requires is, if it's coming from the end user, then the end user has to have a good data gathering system in place that meets one of the standards identified in 1508. So for example, the IEC 6300 for gathering field data, because we have to make sure that the data is accurately gathered, that we've properly classified failures. Because what happens in reality is a lot of failures in the field often get classified as systematic and not as random. And when we come to do the PFD average calculations, we're looking at the random failures to include in that. So if we haven't documented our failures properly, we're going to have potentially unrealistic and optimistically low random field failures. And this does happen. And so the general rule of thumb, again, is all failures should be treated as random until proven otherwise. And that way you don't lose any of the random failures. It may be that some of the failures turn out to have some systematic issue later on, but initially you're recording them as random. So we need to satisfy that random hardware failure rate. And somebody this morning said to me, one of the questions was, well, the purpose of prior use justification is to prove the systematic. That is true, but we also have to meet the random hardware requirements for the target SIL that we're trying to achieve. So if it's low demand, then we should be meeting the PFD average requirement for low demand. So again, what happens is, because 1511 and 1508 are both performance-based standards, in 1511, they include things that you need to do, but they don't necessarily give you any guidance on specific numbers. So what is sufficient for a given SIL? They don't really include that. So for example, the other thing we have to do for prior use is to make sure that the devices are properly identified with a specific revision number. So if they have any firmware embedded in them, you also have to include not just the hardware revision, but the software revision, the firmware revision. And these must all be under the control of a management of change procedure to make sure that we're properly tracking changes. Fixed programming language devices have special SIL3 application prior use requirements. That's defined in the standard. And again, for fixed programming, we're talking about you can change set points, you can change ranges, either in on a handheld or some simple device. Limited variability language devices can only be prior use justified for SIL1 and SIL2. So typically your RTUs or your logic solvers will be having limited variability language, the application, if you like. So again, if you've got a logic solver and you're trying to do a prior use justification for the logic solver, then you can only really do it for SIL1 and SIL2. The other thing you have to be careful of is with the changes. We've had instances where clients have tried to do a prior use justification for a device, claiming that the device has been used for years in different plants and different in the same application. But when we look at the revision number, we find the revision number has changed, and this is a newer device. So again, if it's a newer device, depending upon the change, if it was a minor change, you might be all right. But if it was a change to the program or a change to the physical hardware, then you will probably invalidate your prior use justification. So you need to be careful with that. So 1511 lists 4 key items that have to be investigated from a systematic point of view, and it says consideration of the manufacturer's quality management and configuration management systems. So that says consideration. It means you've got to look at it, and it says adequate identification and specification of components or subsystems. Again, there's that nice word adequate. What does that mean? And demonstration of the performance of the components or subsystems in similar operating profiles and physical environments, plus the volume of operating experience. Now here again, what does volume of operating experience mean? There's no guidance in terms of the hours that you should be looking at in terms of that. So specifics regarding the extent of the manufacturer's quality audit, the level of documentation, the detail of identification requirements, etc., these are not stated. So this is, again, open to interpretation. So what does this mean in practice? Well, it means that there should be, whether it's the manufacturer or whether it's the end user, there should be good, accurate, and properly maintained records. If the end user is using a tool for tracking and it complies with the 6300, for example, the IEC 6300, then that's a good, accurate way of maintaining records. But again, you've still got to classify the failures properly. The operating environment and application must be similar and justifiable. So for field devices, especially, again, the behavior of the device in the operating environment can be the same between safety and non-safety. So if you're using them in non-safety, provided you can meet the operating environment and application as being the same, then you can count those devices and the hours that they've been operating for. The important thing is that we have to make sure that any failures have been properly investigated, because what we're trying to prevent is systematic failures that could cause dangerous failures. And that's why no dangerous failures should have been experienced in the last year of operation. So here again, if in theory, if the manufacturer's device has been well designed and manufactured, even though it's not certified, then a year of operation without a dangerous failure should be feasible. If it's not, then it's certainly not a device you want to use. From a device usage and performance here, the list of field devices can be used to support claims of experience in operation provided, and here we go again, the list is updated and monitored regularly, So again, we have to make sure we've got proper management of change, we've got proper documentation in place. Field devices are only added when sufficient operating experience has been obtained. So again, the word sufficient, that doesn't necessarily give you a clear indication. Field devices are removed when they show a history of not performing in a satisfactory manner. So again, what does satisfactory manner mean? And the operating environment is included in the list where relevant. So this is important to understand, especially from the performance point of view. And we know that device performance can be highly affected by the operating environment. So again, selection of devices should be based upon the standard talks about adequate performance of an installed sufficient number of devices in multiple installations for a sufficient operating time. So there's all these nice woolly words there: adequate, sufficient, multiple. What does it mean? And then longer operation can help reveal early failures, such as those related to specification. So again, obviously, if the longer the device has been in operation, the more likely, if there are any systematic issues, the more likely those systematic issues will reveal themselves. Again, we don't specify the amount of operational experience to gain credible statistical reliability. And we know that, again, for statistical credibility, we need a large enough sample, and it has to be similar enough in terms of the operating profile and application. So here, what we try and do is give some guidance on this. 1511 has no defined time in use requirement. So what we recommend is the equipment item must have been shipping for at least 1 year without any revisions or changes, or the equipment must be shipping for 2 years without any significant revisions or changes. So as I said, if it's a minor change, that's fine. But if it's a major change in the application or change in the firmware or change in the hardware design, depending on what it is, it may invalidate the prior use justification. From the point of view of operating experience, what we recommend is at least 30 million hours of estimated usage from a minimum of 10 different applications with the same stress conditions equal to or above the average conditions of the application. So this is what we've considered to be a very reasonable and very good way of specifying that. Because again, if you've got a very common component that's used in multiple places in the same application, then you could fairly quickly get to those hours. So we've defined, or we've really derived this from looking at both the 1508 and 1511 requirements. And what we're trying to do is help by providing a practical and quantitative guideline on how to assess this equipment for proven in use application or prior use justification. So when estimating the number of hours in use, one of the other problems that we find is, of course, the equipment item actual installation dates as opposed to when it's shipped. And sometimes when we look at manufacturers' field returns, the assumption is as soon as it leaves the factory, it's in use. When of course we know from practical experience that the device may go on the shelf somewhere as a spare, or if it's included in a system, it will go into storage before the system is ready for installation and application. And that could be 6 months, it could be 12 months, it could be 18 months. And here again, if the actual installation dates are not available for the hours in use estimation, then you could assume that at least 6 months has occurred, and therefore it was 6 months after shipment. That's not a bad approach. Here again, the other thing is, and I had this morning, somebody actually asked me, they said, we have devices that have been running for 20 years without failing. They have a 5-year useful life. Can we do a prior use justification? No, you can't. Because again, once you get outside of useful life, all bets are off. And that's because of one simple fact that everything is based on when we do probabilistic analysis and PFD calculations, and that is the assumption of constant failure rate during useful life. So the bathtub curve, the flat portion of the bathtub curve, we take an average, which is slightly pessimistic, not a bad thing, between where the end of the infant mortality occurs and where the beginning of the wear out occurs. And because of that, in that flat portion, we can approximate by saying that the mean time to fail is going to be equal to 1 over the failure rate, lambda. And that's during useful life. Once you get outside of useful life, that no longer holds true. And everything that we do based upon that will be null and void. So you have to be mindful of useful life. You have to make sure that as the device comes close to the end of the useful life, your mechanical integrity program should consider either replacement or refurbishment of the device. Because if we exceed the useful life, then all bets are off. And again, it should be assumed that no wear out failures are reported to the manufacturer, because here again, how often are devices returned, especially if they're sensors? If the sensor fails, does the end user send the sensor back to the manufacturer for evaluation? No, of course not. Even in warranty, some of the end users tell me, no, we still don't, because it's still too expensive to do that. So once you get outside of warranty, you have no idea how many actual devices have failed in the field or need to be refurbished because of problems. So this is another assumption that gets made sometimes, and why we see some silly failure rates coming out of certain certification bodies. One of the people in the webinar this morning told me they had a certificate for an actuator, here we go again, that had 0.02 fits for dangerous failures on it. And those of you that understand fits and understand what I meant when I said that, you can't believe it. It's probably more reliable than a piece of wire. Well, good luck with that. Okay, so let's sort of summarize this. Studies have shown that the majority of accidents have been traced back to systematic issues. And as I said, typically the systematic will come about because there's an error in the design specification, or wrong component, or anything caused by the fact that somebody wasn't properly trained or they weren't following a proper procedure. So this is why when we don't use certified devices, that we have to do a prior use justification for the equipment we're selecting, because we have to make sure that not just the random failures from the PFD or PFH are met, but also the systematic. And OSHA and ACOMA require manufacturers of hazardous materials to follow RAGAGAP, as we said, recognized and generally accepted good engineering practice. 1511 requires us to justify our selection of SIS and SIF equipment to ensure it meets the systematic capability, and it defines the 1508 certified approach or the prior use justification. And mechanical integrity must be maintained and the equipment either replaced or refurbished before the end of useful life. This is very important. Prior use justification requires sufficient volume of operating experience in terms of hours for the equipment operating in similar application environment. And as we've said, our recommendation is for at least 30 million hours and 10 different types of application, similar application. Prior use requires tracking of the versions to ensure the prior use is based upon the same version of equipment. And that also applies to any embedded software, not just the hardware. And we do need to take assumptions and make them regarding the in-service operational time for the equipment. Now, interestingly, some manufacturers now are including power on hours counters. So once the thing is fired up in the field, then the counter starts counting the number of hours of operation until it fails, and then it stops counting. And provided the failure isn't catastrophic where you can't read the counter, then you can look and see, okay, it ran for 10,000 hours, it ran for 100,000 hours, or however many hours it ran for before it failed. The key obviously is that the operating profile must be similar in terms of application and environment, and it can either be safety or non-safety for prior use justification, as long as the application is similar. And 1508 does provide some good guidance on operational requirements and hours, although, as I said, the exida scheme provides some direction and guidance. So that's it. If you want to know more, utilize our links, and we obviously do update these regularly, and we do provide quite a reasonable amount of information. If you've got any other questions, let's have a look and see what we've got so far. As I said, this morning I had 47 questions. Okay, so if the device was installed on old plants where even the ATEX were used was very different in this kind of devices used in prior. I'm not sure I understand the question here. Again, if you're asking whether old devices can be used for prior use, as long as they haven't exceeded useful life, and as long as the operating profiles are similar enough to be able to say, yes, we can justify this. And I see that there have been some issues with the audio. Is the audio okay now? Okay, any other questions? You can always email me if you do have other questions that you think about afterwards. I'm always happy to answer the emails. Now there's my email address. If you want to ask me a question, feel free. Okay, so the audio is working now. All right, so some of you had a problem with the audio, some of you didn't. Okay, getting some more questions coming in. Good. Where is the balance between ripping out the plant SIS hardware every 10 to 15 years, which is the useful life? Well, 10 to 15 years may be the useful life of the logic solver, for example. It may not be in a SIF, the equipment is different and each piece of equipment will have a different useful life. Typically, you may say that you define your mission time as being based upon when you have to either refurbish or replace your final elements. So I have some clients that use 10 years, others use the 15 years because that's when the logic solver may need replacing. And so in between time though, you'll probably, if your logic solver is 15 years, if your valves are 10 years, if your solenoids are 5 years, then you're going to be replacing or refurbishing equipment different times. And because again, if you do it right, if you're following all the correct proof test intervals and doing all the maintenance correctly, and according to the manufacturer's safety manual, then you should be able to balance it out. Let's have a look here. There's another question that's just come in. It's quite a long one. Given a particular client, they adopt 1508, 1511 midway through the life cycle of the plant, let's say 10 years, and they have an existing install base of equipment. A project is completed to implement SIS, and they want to use existing equipment that may have been still rated at the time. How would you bias or derate the system if the verification activities specifically relating to prior use consideration and allow for install time in the consideration for the system? Well, here again, if they want to reuse equipment, as long as it's been properly maintained and it's within its useful life, there's no reason why you shouldn't be able to do that. If it's exceeded its useful life, then either it needs to be replaced or refurbished before you use it again, if that's what you're asking. It seems that's what's being asked here. So again, if you've got 5 years to go on the useful life, then that's your useful life ticker that you have for that particular device. And again, if you've got a decent field data gathering tool, you can program in the useful life requirements into the tool, so the tool will remind you when you have to replace or refurbish certain types of equipment. Okay, there's another question that's come in here. What is Exida's view on using generic failure data in place prior use where actual field data has not been tracked? Well, again, you can use the Exida generic data because it's slightly more pessimistic, but remember, it doesn't help you from the systematic point of view. It'll help you with the PFD average to see if the device is reliable enough, but you've still got to go through prior use justification to look at the systematic side of things, because that's what we need to do. For old devices, why should quality management of manufacturer devices matter? Well, again, when you say old devices, if you're talking about devices outside of useful life, then it doesn't, because the device shouldn't be used anyway. But you should always be looking at the manufacturer's quality system, because remember this, the whole point of 1511 is to balance risk against your design. So you're trying to meet your risk tolerance with an effective and cost-effective design. When you exceed useful life, you are amplifying your risk. You're exposing yourself to much higher risk because you think you've got a CIF or you think you've got a SIL, but in reality you don't, because you don't have any probabilistic analysis that you can use. So a run to fail strategy, which somebody said they had this morning, is a recipe for disaster longer term. I have low tech limit switches, are 25 years old and have very low cycle rates, so nowhere near end of life. If I buy the same model, it may have the same specs, but let's face it, manufacturers cheapen products for more profit, or USA built is now built in other countries. Keep old, but spares may not be as good. So again, from the limit switch point of view, if they're used in low demand application, then cycle rates have nothing to do with it. You've still got to look at and you may be using the wrong device, because when we consider low demand versus high demand or continuous or something that's regularly switching, low demand is all about static. And what happens with static is that things remain either in an open position or closed position for long periods of time. So what can happen is you can get either cold welding starting to build up, and it's been shown that any mechanical device that's left static for more than 100 hours will start to show signs, depending on what it is, of course, of cold welding, binding, stiction, all of these things which are dangerous failures. So again, if this is cycle rates based upon cycle test data and cycle test failure rates, that's not applicable in low demand and should not be used. And again, we go through this as part of the FSC 100 when we go through the course. Seems as though my audio has dropped out, but I'll follow up separately anyway. Okay, sorry about that. I would be amazed if a valve would last 10 years without overhaul. The design life of most elastometric components is 5 years from date of manufacture. Well, again, but it depends upon the device. Some manufacturers have 10 years, depending upon the device. It doesn't necessarily mean they're all going to be. I know one attendee at the class said they have 7 years because the manufacturer says they need to be refurbished after 7 years. Does Exida deal with ISO 13849? Yes, we do. And 62061s? Yes, we do. I'm not sure if 62061 has anything regarding proven in use, so I'd be interested to see that one. But 62061 does deal with, you see again, the difference between 13849 is it talks about protection layers, PLs, and 62061 talks about SIL, safety integrity levels. So protection levels and then safety integrity levels are different, although they're trying to mean the same thing. So the 62061 is more probably more used outside of the US. The US tends to follow 13849. Okay, what else we got here? We've got one of the requirements of prior use justification devices is the quality management of the manufacturer. If devices satisfy all requirements in site, recorded, documented, why manufacturer quality need to be included in the requirement? Because you don't know how the thing was designed in the first place, and that's why, from a systematic point of view, you have to make sure that there aren't any gotchas in the way the thing was designed. It may perform okay in the field, but that doesn't necessarily mean it's going to prevent you from having a systematic issue as a result of the design. Okay, good questions. Anything else? Otherwise, there are no more questions. I'm sorry some of you had trouble with the audio. I don't know if it was connection at your end or not. Okay. Oh, there's another one, is there? Okay. Now I think we're done with the questions, unless there's any more. I thank you all for your attendance. And again, if you think of anything afterwards, you want to ask a question, please feel free to drop me a line. I'm always happy to respond whenever possible. And if you're interested, want to get some more knowledge, then by all means, look out for the training course that's coming up in 2 weeks or so. It's a live streaming instructor-led. I'm running it. So if you're interested in joining that, then please let us know. It's a pretty interesting course, and it goes through all the life cycle in reasonable detail. So there's a lot to cover. Okay, thank you all. Take care. Enjoy the rest of your day wherever you are.